Okay, this is a quick video from class and the board behind me talking about maneuvering speed and the summary of week 2 material. We started out with this view graph. It's kind of busy, so let's go through it piece by piece. I want to focus on the one thing that I think is really important, and that's the CL max. CL is a function of angle of attack, and the aircraft always stalls at the same angle of attack. Always. The interesting thing is that if you divide angle of attack in degrees by 10, you'll get close to the C sub L. So if the aircraft stalls at 20 degrees angle of attack, probably CL will be close to 2. That's just a rule of thumb. So I'm focusing on a piece of my blackboard where the dynamic pressures are always the same, whether I'm at altitude where lower density air occurs or whether I'm at sea level where high density air occurs. Now this formula is important because the sensor on the airplane measures pressure. It measures pressure. So if I want to see the pressure that the airplane at CL max for stalling, I need to use the equivalent pressure, and that's generated by the equivalent velocity at sea level because that's what the aircraft measures. So if I were to do that and go back to my formula, then I would see at 1G flight, when I'm at 1G in straight and level flight, go back to our week 1 class, I'm flying horizontally where the lift equals to the weight. Then if NZ equals 1, I will stall. I'll have maximum coefficient of lift when this equivalent velocity is a minimum. That's called stall speed, and that stall speed is what the pilot will see on his cockpit, no matter what altitude he's at, because that's the pressure that he is measuring. I could have other equilibrium flights. I could be turning, descending, climbing, right? So NZ does not have to be equal to 1. But if I'm in level flight, then I get the 1G stall speed. So what other stall speeds are there other than that one? Well, if you look at the formulas, if you divide the dynamic pressure at any altitude with sea level, you divide by 1/2 rho C sub L, you can solve for your equivalent velocity. And notice that the ratio of the densities is always going to be less than 1. That's called sigma. The square root of the densities is called sigma. And so your indicated airspeed in the cockpit, which is your equivalent airspeed, your indicated airspeed is going to always be less than the true airspeed unless you're flying below sea level. So what does that kind of look like? Well, if I am not flying at my stall speed for 1G, suppose my NG, suppose I have a 9G airplane and NZ goes to 9. Well, I'll stall the airplane because if I'm at stall speed, I can't pull more than CL max at 1G. But what if I'm going faster? If I'm going 3 times the stall speed at 1G, if I pull that 3 out of the square, that gets 9 here. So the 9 and the 9s will cancel, and at 3 times the stall speed for 1G, I'll be at CL max. So I'll be able to pull 9 Gs at 3 times the stall speed for 1G, right? And that's the maximum. Then I'll stall it. Well, right there, the lowest airspeed that I could pull to maximum Gs is called the maneuvering airspeed. If I go faster than that, I'll be traveling down this curve, and I'll be able to pull more than 9 Gs. But when I do that, I could pull the wings off the airplane. So the red line airspeed is as fast as you. When you're going the red line airspeed, you can pull more Gs than the wings can take. So between maneuvering flight and maximum red line flight is a dangerous area where the pilot could fly, but he may not. He gets to be careful that he doesn't pull more Gs than the airplane can take. Well, that's it. That's good. Good luck with